Did a bit of bookwork on what's been happening at NIST, and as I'm sure everyone in this group is aware, NIST sets the standards for cryptography that's used worldwide. Um, and they've been aware of the potential of a cryptographically relevant quantum computer appearing at some point in the next 10 plus years. Uh, and they're also conscious of the fact that any major change in this area is going to take at least 10 years to push out. So it's a good idea to get ahead of the curve and build a lot of contingency into your planning. Um, Looking at what they had overall in terms of published standards around cryptography, um, there's a couple of standards that were clearly going to get compromised by quantum computer. Based around RSA or elliptic curve ciphers. Um, so one's to do with the typical key exchange mechanism, and then also one's related to digital signing. So this slide I pulled from the original NIST presentation where they decided to start the post-quantum initiatives inside NIST, which demonstrates what is susceptible to a quantum computer and what they believe to still be theoretically sound moving forwards. Um, Here's a bit of a timeline just to put everything in context in terms of what NIST did. Starting off with that initial report just back in 2016 and the beginning of a competition to try and find the next generation of quantum resistant, quantum safe ciphers. Um, so over the course of 4 years, they whittled down 69 submissions to 7 finalists, um, and ended up selecting four algorithms to move forward with in 2022. One of those is key exchange mechanism, Kyber, which has become MLKEM, and then the other three digital signing algorithms, codenames Dilithium, Sphinx Plus, and Falcon. They've become MLDSA, SLDSA, and Falcon hasn't actually been standardized yet. We haven't seen a draft. So out of those four algorithms, three were standardized in 2024. The fourth, a draft of the standard is expected this year. Um, and then after the draft, the finalized version will follow. Another interesting aspect is the fact that there's a second key exchange mechanism algorithm coming, which is HQC. So there's actually five algorithms in play, of which NIST have standardized three, and two are still coming. Um, they've also produced a draft of post-quantum cryptography transition, which is IR 8547, which is currently in public draft. And the final version of that is expected to be published this year. That's more of a guideline for how all of the cryptography that's out there in the wild should be upgraded to quantum safe equivalents.
Stephen, it's Ben from Peaky Shield here. Just a couple of points there. Just been talking to NIST recently myself. So Falcon is fully drafted, is ready to be published. US government shutdown fairly recently kind of pushed that timeline back, but we are expecting that anytime now. HQC may not hit in 2026. The current NIST estimate is some point in 2027. It's not even final whether they're actually going to standardize it or not. But the industry seems to want a backup chem mechanism, so it looks like they probably will at some point. So.
Good, thank you. Anybody got any other comments on that timeline? Okay, and then I did a little bit of digging around just to provide some stats to compare chems and DSAs. The main heavy lifting of key exchange is expected to be handled by MLChem. The chaps at Wolf SSL did some performance comparisons of MLChem versus the existing um, non-quantum safe algorithms and found them to be performant in terms of CPU cycles. So that's good news. Um, I pulled the stack memory from an academic paper. The references in the top right, where it looks like 3K, typically up to 4.5 is required in terms of RAM, which I think might be a problem for some memory constrained devices. I saw there's a um, a library that's been produced for constrained devices, which suggests previous algorithms could be run at 700 bytes of memory. So maybe 3,000, 3,800, 4,400 is a bit high. I don't know. Do people on the group have magic numbers in mind in terms of what they think a cryptographic cipher needs to hit to be useful across some of the memory constrained devices in IoT world?
No, but it definitely needs some research because there are a lot of devices that go into the built environment, as myself and Steve talked about a few days ago, and many of those are, simple sensors for just detecting people around or detecting limited amounts of physical environmental changes, and many of them increasingly run on energy harvesting systems, so they don't have to be wired in or batteried, and so on. So that would require a fair bit of work to work out what the minimums might be.
There's quite a lot of work our team have done with a number of vendors on optimizing a number of these algorithms. They can be optimized quite heavily for different target architectures. So, I think if you want to do a secure boot and you want to verify only, for example, you can get away with 20 kilobytes of stack and like 4.5 kilobytes of RAM, right? So you can get it squeezed down, but you do require a bunch of optimizations, and obviously the trade-off there is sometimes performance. Yeah, I mean, maybe in a future session I could get one of our team to kind of summarize some of the optimizations that have been done, which might be useful for everyone.
Yeah,
Yeah,
that'd be great though.
it would definitely be worth getting probably. This is, I guess, to Chris and Steve as the drivers of this group to get involved. Some of the and I'm sure there are other industries, but my background is in the smart build environment. There are a goodly number of manufacturers of equipment that could be usefully pulled into this conversation, because it's obviously not only what they've got, but it's what they're planning to have. That probably they need to be in this conversation to make sure that they can ultimately comply, since they're going to be impacted, particularly in Europe, with CRA and so on. And I guess quantum is going to lean very heavily on them for that in terms of this conversation. So yeah, we probably need a few more partners, Chris, to this conversation. And just for your information, that since Steve and I have been speaking since the last meeting, I've also been talking to my American colleagues about post-quantum cryptography, what they know, what they understand, and what do we need to learn to start preparing a whole global industry who are already struggling with cybersecurity issues of doors flapping open in many smart buildings that they don't understand and don't realize that are now being attacked. And now this subject matter, very important, is creeping up on them. And bearing in mind that their turnaround time on equipment in buildings is somewhere between 10 and 15 years, they probably need to be right on the front edge of this conversation to figure out where they need to be thinking.
Yeah, for sure. And I'm sure Doug will get into that more when we chat about the threat space in 10
Yeah.
minutes or so.
Anyway,
So
just
yeah,
just feeding a little flavor into the conversation, my side.
yeah, no worries. Good input. And then yeah, just the other side of the cipher world from the key exchange mechanism, digital signatures. the three different flavors. Two have already been standardized. Falcon's coming this year, as Ben said. You can see the different metrics there. MLDSA, higher performance in terms of CPU cycles for actually running through the algorithms, but has pretty hefty stack memory requirements, which I think might be a problem for some of the devices that were mentioned. SLH DSA looks much better from that perspective, and then Falcon would be even better still, although that very compute expensive key generation maybe is a problem in some use cases. Anybody got any comments on this slide that they just want to surface?
I think again, it's just the question of the design space as we knew it has changed quite considerably, and there are different decisions to make. And what we're finding in a lot of implementations right now is that there's as much architectural decisions that need to be taken rather than just algorithm selections. To give you an example, looking at and smart meters network, you've got all sorts of requirements, like every operator in every energy company can connect to every single smart meter set up in every home. What that means is you have a large amount of key generation, when actually the information that you're getting at isn't completely and utterly time critical. You could make other design decisions that make that process much easier, drag that data back to the center at a regular interval, and therefore reduce the amount of key exchanges in the network, and therefore make better algorithmic choices for what you want to secure that with. Because ultimately the threat is not about anyone's meter reading, the threat is actually about the ability to isolate the power to that particular property. So again, just kind of pointing out that with all these algorithms, and probably more to come, by the way, this design space is much more complicated than it was. So it's a slightly one step removed, sort of take a one step back view of the overall thing rather than just pure algorithmic choice.
Yeah, so when you think about the algorithms, you need to think about the overall system design and the use case, and whether there's a change in the workflow that means that you're no longer so constrained around the algorithm. Yeah, that makes a lot of sense.
And I guess one other thing just to throw in, just to be a pain, obviously that's fine if you're sitting in a country like the UK that backs the NIST standards 100%. If you're sitting in a country that actually has its own preferences, like Germany, for example, which has some preferences for some other algorithms, and obviously then you take somewhere like Korea that has its own standards altogether. If you are shipping internationally, you may have even more design considerations to make and even more algorithms to take into consideration too.
It's a very good point. Okay, and then my last slide, just pulling out the structure of the transition plan, IR 8547. NIST is suggesting that they will officially deprecate the ciphers in 2030 and they'll be disallowed in 2035. So got a 4 and 9 year time frame now. When they spill out all the relevant crypto techs, no real surprises there. Not quite sure how one upgrades the entire PKI and other infrastructure, but that's going to be a bit of a challenge, I suspect. And then considering migrations, interesting use cases, and I think the section on the PQC classical hybrid protocols is quite interesting because it lets you say layer a Falcon inside an existing classical protocol that is NIST standardized, and then say the entire thing is NIST standardized, even though they haven't finished the Falcon standard yet. Or maybe there's some of the esoteric use cases around, especially when you consider memory constraints, where that would be useful. Food for thought on that one, I think.
And bear in mind that on those hybrid schemes, there are still standardization efforts going on at IETF, nearly there. But also Etsy have also released their own version, because there are a couple of different ways you can hybridize these things. They have different pros and cons, but we don't yet have an industry-wide standard. for how to approach hybrid. And again, going back to my point on international standards, different countries have different views on France, Germany, and the UK differ in terms of their views on how to use hybrid and when to use hybrid and if to use hybrid at all. So there's another complication to that design space, I'm afraid, too.
Do you know of a good use case description document that the standards bodies have produced to help frame that work, Ben? It'd be good to. I'd enjoy reading it.
I don't off the top of my head, but I can go away and ask our research team to dig one out. That's for sure. Quite happy to share.
Cool, thank you.